Hey guys, today we are going to talk about the standard form of a quadratic equation. And again, quadratic equations are the ones that create the nice parabolas that you've been seeing graphs of or been working with so far. All right, so the first thing you need to know is what the standard form looks like. You got a preview of it last section, but here it is. Y equals ax squared plus bx plus c. And when you're working with the standard form, the A, B, and C, those are constant. So you'll see a number substitute in for the A, a number substitute in for the B, and a number substitute in for the C. But the x squared, the x, and the y, those will remain variables. You'll just see numbers in there. Now, the cool thing about the standard form is that whenever you're looking at the equation in standard form, you can just look at it and identify what the y-intercept is going to be. The y-intercept is always going to be in the spot 0, comma, whatever that c value is. So this is that c. So you can just look at the standard form and pick the y-intercept out. Cool. But we can't find the vertex quite as easily. We're going to have to do a little bit of work whenever we're in standard form. So there is a formula for that. So remember that the vertex, PS, like over here, let me write a special note because I didn't give myself enough room. The vertex is h, comma, k. The h is the x part of the vertex. The k is the y part of the vertex. So to find the h part of the vertex, we're going to use a formula. The opposite of whatever your b coefficient is, divided by 2 times the a coefficient. So that's how you find the h part. To find the k part, that's just a squiggle line for dividing. The k part, you're going to find f of whatever the h was. So that means take your formula and substitute in your h value in for x, and that will help you find the k part. All right, domain, I know I skipped axis of symmetry, but domain is still negative infinity to infinity. The axis of symmetry is still x equals whatever the k value is. And the range, again, it depends on how your parabola opens. So if your parabola opens up, the range will be from that k value to infinity. If the parabola opens down, then your range will be negative infinity until the k value, with a bracket on the k. Now, how do I know if it opens up or it opens down? You look at this a value. So also note this a value here is the same a value that you saw in the vertex form. So the a in standard form is the same a in vertex form. Is the same a in vertex form. Now, let's look at your notes. Now, as you take notes, we can look, these notes are on page 68 in your workbook. Okay, so follow along and take notes as we work through here. All right, so example 1 says find the vertex of the graph of the function f of x equals x squared minus 8x plus 5. So the first thing I need to do is find my vertex, and I want to remember that my vertex is in the form h, comma, k. All right, so let me work on finding the h part. H is, here's the formula again, the opposite of the b divided by 2 times my a coefficient. So b is the coefficient in front of the x. So the opposite of negative 8 is positive 8 over 2 times the a coefficient, so the coefficient in front of the x squared. there's nothing in front of the x squared, you can assume it's a 1, so 2 times 1. And 8 divided by 2 is 4. So my vertex is 4, comma, and now I have to find the k value. So to find the k value, and like I'm separating k, I find that by finding f of the number you got for h, so f of 4. So that means I'm going to take my f of x formula, and anytime I see an x, I'm going to substitute in a 4. So 4 squared minus 8 times 4 plus 5. So 4 squared is 16 minus 32 plus 5. Oh, let me grab my calculator. I think it's negative 11, but I'm just double checking. 16 minus 32 plus 5, negative 11. Yes, okay, I get negative 11. So my vertex of this form is 4, negative 11. Now this h equals negative b over 2a. You're going to need to remember that because we're going to be using that a lot. Okay, next. Now we're going to graph given the function in standard form. So we're going to use key features. Now some of the key features we know are the ones that we listed above. So I'm going to use the key features up here. Vertex, y-intercept, axis of symmetry, domain, range. I'm going to use all that to help me graph this quadratic function. So yes, I could type this into Desmos, but you're also going to need to be able to do it by hand because, you know, sometimes you have to pick out points, sometimes you have to give explanations by hand. So let's do this. All right, well, first of all, I know that it's in standard form because I see an x squared and an x. So it is in standard form. The other thing I can look at is I can see that c is negative 1. So right away that tells me that my y-intercept is at 0, negative 1. So I'm actually going to go ahead, no, because I don't know where my vertex is. Let me wait a minute. Okay, now let's find the vertex. Color here. Vertex. T-E-X. Okay, let's find the h part. So h equals the opposite of b divided by 2 times the a value. B is the number in front of the x, so the opposite of negative 6 is positive 6. Divide that by 2 times my a coefficient, which is in front of the x squared. There's nothing there. I assume it's a 1. So 6 divided by 2 is 3. So I know my vertex is at 3, comma. Now I have to find the k value. So to find k, I'm going to find f of the h, 3. Which means take 3, substitute in for each x in the formula. So 3 squared minus 6 times 3 minus 1. So that would be 9 minus 18 is negative 9. And negative 9 minus 1 is negative 10. So I have a vertex at 3, negative 10. Okay, so now I'm going to plot these. Whoa. Let's erase that mark. Okay, so I'm going to try to draw these as best as I can. I see that my vertex is 3, negative 10, which is pretty low, so that tells me I should probably put my x-axis up here. 3, negative 10, maybe put the y-axis somewhere like right there. Whoops. Okay. So 0, negative 1 is this point right here. Here's my y-intercept. And then 3, negative 10. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Add a point. So negative 10. Okay, now the axis of symmetry goes straight through the vertex. So to get my next point, Since it's an axis of symmetry, I can reflect this point across the axis of symmetry right here, and then I can draw in my parabola. All right. Example 3. A water balloon was thrown from a window. The height of the water balloon over time can be modeled by this function. What's the maximum height of the water balloon after it was thrown? So maximum height. Okay, well, let me look at this graph. Time is the x-axis, height is the y-axis. So maximum height is going to be a y value. So I can look and I can spot that it's about right here. But you see how this point isn't exactly on a coordinate? So I'm going to need to do some figuring here to figure out what the maximum height is. So that tells me, since I probably want to know this point, I should probably figure out what the vertex is. So let's find the h value. H equals the opposite of b divided by 2a. So the opposite of b is negative 160. Divided by 2 times a, or 2 times negative 16. Negative 160 divided by 2 times negative 116 is 5. So I know my vertex is 5 comma something. To get the k, I'm going to substitute 5 in for both of these x's. So that will be negative 16 times 5 squared plus 160 times 5 plus 50. So for k, I'm getting about 350. I'm going to double check. Let's see, does that look like 5, 350? Doesn't look like 350. Let me think about this for a second. It's 450. I miscalculated, so let me change that. This is 450. Okay, so my vertex is 5, 450. Okay, so now double check. 5 is in between 4 and 6. 450 is in between 400 and 500. Yes, okay, so that looks right. All right, so then let me answer the question. What was the maximum height of the water balloon after it was thrown? Okay, well, maximum height looks like it's the y value. So the maximum height is 450 feet. So I would say 450 feet is the maximum height. And then how long did it take for the water balloon to reach its maximum height? Well, the length of time is the x value, so 5 seconds. All right, next is really fun. You're going to be asked to write the equation of a parabola that passes through points 2, negative 12, negative 1, negative 15, and negative 4, negative 90. So the way I'm going to show you how to do this is with something called quadratic regression. So you're going to need your Desmos calculator for this. Okay, and what you're going to do on Desmos is you are going to plot these three points. We don't have an equation, but we're going to do a table. So hit the plus sign and do a table, and notice there's x1 and y1. Okay, so the x1, I've got 2, negative 1, negative 4. And for the y points, make sure you coordinate them. So 2 has a y value of negative 12. Negative 1 has a y value of negative 15. And negative 4 has a y value of negative 90. Okay, so we've got the points. Then I need a regression equation. Now, if I look, I'm going to need to zoom out a little bit, but you see how the points are plotted? 2, -12, -1, -15, and -4, -90 is right here. So I need an equation for the parabola. And if I want to change settings, maybe I want to go like the x-axis -3, 3, maybe -5, 3. Must have typed in 2. There we go. Now I can see my points a little bit better. So those are the points at graph. Now if I want to use a regression equation, what a regression equation is, it's a line of best fit. And so it's a way to get a formula that will match your points that you have. So I'm going to do this way. You'll need to type y1. So I have a y1 here. When you type the 1 subscript automatically enters itself. Then you'll use this tilde symbol. That's the approximate. We use that whenever we're doing regression in Desmos. And then I'm going to type in my standard form. So ax1 squared plus b x1 plus c. Notice, oh, there's a nice curve that fits. Okay, so you notice this looks like the standard form, except instead of the x's, it has x1 because that's why we're using a table for x1. Instead of the y, it has y1 because we're using a table with the y1 values. Type this in, it will give you a nice parabola that fits the points that you put on it pretty well. And this r² number, the closer that is to 1, that means that the equation that got generated, the closer that is to 1, the better the fit. So we see that this r² value is 1, which means it's a perfect fit. So all our points actually form a perfect parabola. Now this a, b, and c value, those are my coefficients for a, b, and c. So when it says write the equation of the parabola, I'm going to record these values. A is -4, b is 5, and c is -6. So I'm going to come over here. A equals -4, B equals 5, and C equals -6. Okay, so then my equation for that parabola is y equals -4x squared plus 5x minus 6. There's my equation. You can also do that with more data points. So let me pull Desmos back up here. Clear those out. Now I'm going to type in another table with those data points. 0, 0.2, 0.4, 0.6, 0.8, and 1. And then 10, 11.76, 12.24, 11.44, 9.36, and 6. Ooh, that's looking pretty nice. Looks pretty parabolic to me. So let's come up with the equation. y1, make sure you use that tilde, ax1 squared plus bx1 plus c. And make sure you enter it just like this or it won't work out. All right, so this time we're seeing a is -16, b is 12, and c is 10. So the equation for this parabola that fits this situation is y equals -16x squared plus 12x plus 10. Isn't that wonderful? Now, let's look at the problem and answer the question. A fan threw a souvenir football into the air from the top of the bleachers towards the bottom of the bleachers. The table shows the height of the football in feet above the ground at various times. So it looks like the football started here, and then it got thrown up and then came down. If the football wasn't touched by anyone on the way down to the ground, how long did it take the football to reach the ground after it was thrown? Now, if a football is on the ground, then its height would be 0. Now, there's 2 times the football has a height of 0, at negative 0.5 and at 1.25. I'm not going to include the negative 0.5 because that would be like going backwards 0.5 seconds in time. So we're going to exclude that point. But I will include the 1.25. So after 1.25 seconds, the football hits the ground. So I'll write that here. It took the football, if I can write. Oh no, oh no. I'm pressing a button somewhere. I must be pressing a space bar. Well, I'll just have to say it out loud. It took the football 1.25 seconds to hit the ground. All right. And then on our habits of mind, how many points does it take to determine the equation of a quadratic function? You're going to need at least 3 points. Why are there so many points used in example 4? The more points we have, the more information we'll have about being able to draw a quadratic function. But you do need at least 3 points. So anytime you have 3 points, then you can use the quadratic regression method. All right. So good luck with this. You're going to have an assignment on Math Excel. If you have any questions, please feel free to contact me. Have a great day, guys.